Okay, Monday we present how to determine the discharge. So we have the discharge and can be represented by uh, the area multiplied the velocity. And since we have the discharge, so we can determine the mass flow rate. The mass flow rate can be represented by the density multiplied the discharge. Okay, so this class, we move to the next. First, we introduce two methods. As I say, the first one is the systems, but we focus on the closed systems, and the sequence is the control volume methods. Okay, so as the cartoon figure showing here, you can see this is the closed systems, and the closed system can be changed for the system boundaries. The dashed line is the system boundaries, and as you can see, if the piston moving downward, and the system boundary will be changed. But the ideas for the closed systems is the mass cannot cross the boundary of a closed systems, and then the boundary of the closed system can move and deform. So that the closed system is based on the Lagrange concept. As I say, Lagrange concept is you pick up the fluid particle, and then you can observe the fluid particle change it with the different time point. That means because the closed systems, we fix the system boundary with the dashed line showing here, so we can easy to pick up one fluid particle and check the particle trajectories with different time points. Okay, but how different for the control volumes? So you see, this is the control volumes defined by the dashed line, and the dashed line showing here, we call that is the control surface. But how different you can observe here is the control volumes of the boundaries control surface in here, and then you have some input and you can have some output. So the significant difference compared with the closed systems is the control volume. We can have the mass exchange along the boundary, and the boundary here is the control surface. But the closed systems cannot have the mass cross through along the boundary of the closed systems. And because we fix the control volumes in here, okay, so the control volume, the idea is based on the Julian concept. What is the Julian concept? The Julian concept, we fix the point and we see what happens at this point. As I said before, if we put the, for example, we put the wind speed meters at this point, So we can observe the wind speed at this point for a different time point. Okay, so and because we define the control volume already, so the control value didn't change with the time. So we always focus on the physical property changes for this control volume space. So this is based on the Julian concept. And the table summarize the system analysis tools. Okay, so if you have the one systems and you can divide it to your concept, first one to the control volume, CV, and or you can use the closed systems. And then you see usually the closed system you can pick up one particles or you just collect the particle page. Okay, and usually because the closed systems cannot have the mass closed through the boundary, so it's very easy to apply to isolate systems. You see no work or heat transfer at the boundaries. Because also the closed systems based on Lagrange ideas, so it's very easy to apply to the rigid body because the Lagrange need to pick up one particle and analyze with this particle for a different time point. But the control volume is based on the Julian ideas. So we always focus on one space and discuss the physical property change in the space. Okay, so but we here point out the control volume can fix or can be deformed. Okay, so this is also just a table summarize and make a comparison between the closed systems and the control volume approaches. Okay, again, so the idea is we can divide it, the closed system focus on the Lagrange approach, and the control volume is based on the Julian approach. And the closed systems, the mass cannot cross the boundary, but the control volume can transfer and cross the boundaries. Okay, so application is quite similar. So you can apply to the solid mechanics, fluid mechanics, thermodynamics, and the control volume usually didn't apply to the solid mechanism, but also can be applied for the fluid mechanism, thermodynamics, and the other thermal science. Okay, so even though we have two tools and the closed system and the control volumes, but the previous slide we only focus on the physical property is the mass. But here we can apply two approach for any matters. So we divided the physical property into two types. So the first one is intensive properties, and the second is extensive properties. So usually we call what is the intensive properties, such as the pressures, temperatures, densities, which is the properties independent on the amount of the matter present. Okay, and we see what is the intensive. properties. The mass, moment, energies that depends on the amount of matter present. So I pick up two properties. First is density and the second is mass. What is intensive? Is independent on the amount of the matter present. So you see the density rho can be divided by the mass, okay, divided the volume. And if we change the mass, okay, we change the mass, maybe the mass is increased, but the density didn't change it because the volume also increased. So we call the density is intensive. That's because the density is independent on the mass. Even though the mass changed, but the density didn't change it. But here we call the mass is extensive property because the mass will change with the mass. If we discuss the momentum can be divided by the mass multiplied the velocity. So as we know, if the mass changes, the momentum will be changing. So that's kind of the properties such as mass, momentum, energy. They are extensive properties. Okay, and you see the bottom center showing here. Usually the ratios between two intensive properties is the intensive properties. So for this slide, we define the extensive property is capital B, and the intensive property is small b. So we define the B is equal to the mass over B. Okay, so so we know if the mass multiply the small b will equal to capital B. So intensive multiplied by the mass is equal to extensive property. Okay, so and here we define the control volumes. This is the extensive properties in the control volumes is equal to the intensive property multiply the small mass difference, and we use the integration operators along the control volume space. Okay, and you see the dm, the small mass, is equal to the rho multiplied the dv volumes. Okay, so this is the dm. So we can define the extensive properties in the control volume follow this formula. So, and now we discuss the methods closed through the control surface CS. So as we pick up the control surface already, and the inside is the control volume, and the dashed line is the control surface. And in case we have the cross section area 1 and the cross section area 2, and we have the two flow field. So the V1 inside to the control volume and the V2 outside the control volumes. So and if we know we have the low density 1 in here and the low density 2, and the cross-section area is A1 and A2, and we assume the flow directions is parallel to the normal factors of the cross-section areas. So we can define the mass flow rate for the one cross-section 1 is the rho 1 multiply the A1 and then multiply the V1. So as I mentioned before, the cross-section area multiplied the velocity is the discharge Q, and we multiply the density, so this is a mass flow 1. And the mass flow rate 2 is also equal to a rho 2, A2, and the V2. So usually we call that is, here is the outflow, and here is inflow. Okay, so we have the inflow, we have the outflow, and we define the outflow minus inflow is the net mass outflow rate. Okay, so you can summarize the net mass outflow rate is equal to the m rate 2 minus m rate 1. Okay, but if we consider the dot product, okay, and so you see here what is the mass flow in here is the cross-section area factors multiply the flow velocity direction factors. And this is also the velocity factors multiplied by the cross-section area factors. But you notice that for the inflow cross-sections, the flow direction is right, but the normal factor of the cross-section area is left. So if you use the dot product, so we have the negative sign for the inflow mass rate. Okay, but for the outside part, the normal factor of the cross-section area is the same directions with the flow directions. So there is the positive. So the net mass outflow rate also can be represented the same formula compared to the previous slide. So even though you use the normal, you use the dot product to compute the net mass outflow rate, we will have the same solutions. Okay, so we can also define the mass flow rate for the extensive properties like the B dot net showing here. So we can we defined it along the property changes along the control surface. So as you see here, we have a small b, and as I mentioned, the small b and multiply the right hand side. We need to right hand side showing here is the mass flow rate. Okay, so we can define it the intensive property multiply the mass flow rate will equal to the extensive properties rate. cross through the control surface. Okay, and we define this as extensive properties rate for cross through the control surface. So this is a little bit difference. Before we defined it, the B, what is the BCV? The BCV is also can be used the integration operator, but along the control volumes, and we still have the B and divide multiply the DM, and we can rewrite the DM by the rho dV volumes. Okay, so if you compare the BCV and the B dot net here, there is the BCV, there is no dot product, but the net of the B dot, we have the dot product operators. So it is a difference compared with the BCV and the B dot net. Okay, so now we wondering to understand the total extensive property changes in the closed systems, and how can we analyze the B extensive property changes with the times. So this is the BCV at the T time point, and after the delta T, and the BCV change to here. Okay, and at the time point D, and this is at the time point T plus delta T. And so here we have the sum inside, the extensive properties inside, and there is the extensive properties outside. Okay, and the sentence tell you the shaded area is our closed systems extensive properties, and at the delta T, and the closed systems extensive property change. Okay, and the dashed line is the control surface, and the inside the dashed line is our control volumes. So for this problem, we fix the volumes. Okay, so we write down some equations. The closest systems for the extensive properties. T is BCV, the extensive inside the control volumes, plus the B in here. This is for the time, the T times, and the closest systems T plus delta T in here is we have the control extensive property in the control volume, but right now the time point is T plus delta T. Okay, and we have a small piece outside here. So we compute the dB cross systems dt. So we can plus the B cross system T plus delta T minus cross systems at the time point T, and we divided the delta T. Okay, so we expand the formula showing here. The cross system can be represented by the BCV T plus delta T minus BCV T times, and because we have the out and we have the in, okay, and we still keep the delta T on the bottoms. So the total extensive property in closed system change with the time, and you can divide it the formula into two parts. This is the first one, and this is the second one. Okay, so the first one in here, this is only focused on the extensive property changes in control volume CV and change with the time, different time points. And the second part in here is totally similar to the B dot net. So we have the B out. This is B out rate, and this is B in rate. Okay, so usually we call that is inflow, and this is the outflow. So for this part, we can call that the extensive property is the flow outflow rate, but for the net. So the net is out minus in. So finally, we can summarize. Our formula is the dB closed system dt is equal to the BCV dBCV dt and the net outflow rate of the extensive properties. And we know that the BCV is also equal to the B integration operator along the control volumes and small b multiplied rho dV. And the B dot net, we know that is the control along integration operator along the control service, and we have the B, and we have rho B velocity factors dot producted by the cross-section area factors. Okay, so usually we call that is the Reynolds transport theory. Okay, and notice that there is the dot operators, not the scatter. So for the some physical properties exchange along the control service, we need to consider the dot product operators. Okay, so here the slides just introduce the physical meanings for the Reynolds transport series. So as we mentioned, the right side is the dB closed system dt. This is based on the Lagrange concept. Just fix the one point and check the point at different times. So usually this is for the cross systems, and we easy to pick up one particle and check his this trajectory. And the right hand side is based on the Urian concept, because we define the control service boundaries, and the inside is the control volumes. Because we fix the control volumes, it's similar ideas for the Urian concept. We fix the one point, and we didn't change the point. We just observe and to see what happens at this point. So we fix the control volumes. So the idea is The left side is the rate of the change of the property B in the cross distance is equal to the rate of the change of the part B but in the control volumes, and plus the net outflow of the property B for the control surface. Okay, so for the following ideas, I showed two cases, but even though we didn't know the nano transpose theory before, but the following two case exercise we still can do analyze by our basic background. As you see, this is one of the problems. We always have some insight, and this is the inside discharge for the CH4, and the CH4 discharge flow just flow into the rivers. Okay, and I tell you there is evaporations, and the evaporation rate just follow these numbers, and the problems we need to answer the questions is what is the concentration of the CH4 after 1 hour? Okay, after 1 hour. So we know there is the input and there is the outflow. So we have the inflow here, and we have the outflow here. And I tell you the surface area is 400 meters squares, and the total initial water volume is 500 cubic meters. And this is the initial concentrations of the CH4. And then we need to answer how the concentration changes after 1 hour. So we compute the initial, the mass of the CH4. So we have the C zeros in here. Okay, we have the C zeros, and if the C zeros multiply the initial volumes, and then we can compute how many mass for the initial CH4. So notice that the unit is a little difference. So the L is liters is equal to 10 minus 3 powers cubic meters. Okay, so that we know that the mg divided L, usually you can transfer the unit to the g divided m cubic. Okay, so here we know the C0 is 0.5, and the unit can be changed to the G divided the meter cubic. Okay, and multiply the total volumes is 500 cubic meters. Okay, so you can use your calculator to compute. The answer is 0.5 multiplied 500 is, so here is the 250 G. Okay, and what is the mass from the inflow? So we have the discharge in here, Q in discharge, and multiply the C in, okay, and how the time changes is the 1 hours. So we have the 1 hour changing the time, multiply the time. So first, the Q inflow is 0.02. Sorry, I always have the horizontal line. And the unit is meter cubic divided seconds. Okay, and the concentrations is 10 G and meter, 10 G and meter divided the meter cubic. And what is the time? Time is 1 hours, so it's equal to the 3600 seconds. And you can compute how the mass contributed from the inflow. So use your calculator, 0.02 multiply the 10 and then multiply the 3600. So it's equal to 720 G. And what is the out? What is the out? So we know that the evaporation rate is 0.02 shown here, and the unit is the mg divided the m square, and also divided the second over 1. Okay, and because we have the area in here of the water surface, so we multiply the 400 meter square, and we have the 1 hour time, so we multiply the 3600 seconds. Okay, and how changes flow out for the mass. So use your calculator, 0.42 multiply 400 and multiply the 3600, and we here is mg. So the final answer need to divide it 1000 to convert mg to g. So here the mass is 604.8 G. Okay, so we have a M0, M in, and a minus N out. And the how changes of the delta V. Okay, so the delta V, we know the inflow discharge is Q in showing here. So we have a 0.02 cubic meter per second, and after 1 hour. So this is 1 hour seconds. Okay, so we know how changes. So 0.02 multiply 3600. So the volume change is 72 meter cubic. So right now we can compute the concentrations after 1 hours. So the M0 is 250 plus, and the M in is 720, and the minus M out is 604.8 divided the total volume. The total volumes is 500 plus 72, and then you can compute the concentrations is 0.64 G per meter cubic. Okay, so you take a look. This is the concentrations after the 1 hours, and this is the concentrations for the initials. So the concentration is increased. So we need to notice that if this is the inflow conditions, well, that the concentrations of the CH4 in water, river waters, will increase. So it's very dangerous for the rivers. Okay, and the next problem is the seniors. Again, so we still have the inflow here, and we have the outflow here. And the dashed line is our control service, and inside the dashed line is our control volumes. Okay, and I tell you, there are some decay rate with action with the chemical response, and is 0.06 G per second. Okay, so in the curved systems, the decay rate is minus 0.06 gram per second. And the questions we need to answer: what is the change rate of the contaminations in the rivers? So the problem in here, we are focused on the DPD BCV. We need to answer the questions for this DBCV okay, but as we know, we are discussed for the concentrations. So actually, we based on the Reynolds transport series. The small b in here is equal to 1. Small b in here is equal to 1, and we know the capital B is equal to the B multiplied the mass. And because our small b is 1, so we know that the capital B is the mass. So now we are discuss with the mass. Okay. So we know we need to answer how mass changes with the time. We didn't know, but we know the changes, the mass in the closed systems. This is a change caused by the chemical response actions. So, and this is in the closed systems is equal to minus 0.06 G per second. So what is this part? This part is we call that is the mass rate, the net outflow mass rate. Okay, so the net of the mass flow rate is equal to the out minus the inflow mass rate. Right now we have the out in here. So what is the out? The out is Q, is the Q out multiply the C out minus the Q in multiply the C in. Okay, so we have the discharge out is the 10 meter cubic per second multiply the 0.05 G meter cubic minus the Q in. Q in is the 0.03 meter cubic per second multiplied 20 G meter cubic. So you can use your calculator to compute the answer is 10 multiply 0.05 minus 0.03 multiply 20. So the answer here, the net mass flow rate is minus 0.1, and the unit is G per second. Okay, so we have the closed system mass rate changes is minus 0.06, and the net of the mass outflow rate is minus 0.1. So we just summarize the equation. The left-hand side is minus 0.06, and we didn't know the mass in control volume change with the time. And the right-hand side is the net outflow mass is minus 0.1. So finally, the mass in the control volume change with the time is the minus 0.06, plus 0.1. So it's equal to the 0.04 G per second. Okay. So this is the same compared to previous exercise. The concentration will increase. So it is not normal for our conditions. We need to decrease the concentrations. Okay, so this value cannot be the positive values for these questions. Okay, so the following slide, we wondering to discuss the second equations is continuity equations. So what is the continuity equations? It's based on the idea is the mass conservations. So we are talking about the concept is based on the conservation of the mass. So that means the mass in the closed systems didn't change with the time. So these items is always equal to 0. So if you go back to the nano transport equations, the left-hand side, the equation in here is always equal to 0. And right now, our intensive coefficient B is equal to 1. And we know that B is equal to the capital B divided the mass. So what we discuss for the extensive property is the B is the mass. Okay, so we rewrite the Reynolds equations for these formulas again. So we follow the conservation of the mass idea. So this item is always equal to 0. So we only have the mass change in the control volumes plus the net outflow mass rate is will equal to 0. Okay, and you can use the continuity equation for represented by the integration operators, or you can write by the summations of the control surface outflow mass rate and the control surface inflow mass rate, but there is the minus. Usually we use the output minus the input, and what is the mass changes in the control values with the time. But sum of the total values will equal to 0. This 0 is based on the conservation of the mass in the closed systems. Okay, so the idea is we move to the net outflow rate to the right hand side and to become the inflow minus the outflow. So that is the accumulations in the left hand side is contributed from the inflow minus the outflow. Okay, and we call that is the mass balance equation also. Okay, so what is the basic idea? The first we need to take a look. The most difficult thing is how can you define where is your control volumes? And since you need to determine the control volume, so you need to depict the control surface first. The control surface is the boundary of the control volume. And then you do the analyze based on the continuity equations. And we call that accumulations. What is accumulations? This is the mass in the control volumes and how change it is with the time. And so we pick up the dash line is the control surface. So this is inside is the control volumes and the boundary is control surface. So in this control volume, what is the mass inside the control values? And the change with the time is equal to the inflow. So we have some inflow and we have some outflows. So this is in. So we have the inflow rate, and we have the outflow rate, and we take the minus in here. If the answer is the positive, so we know that the mass is accumulated in the control volumes. But if the answer is the minus, it's a negative, so we know the mass is flow out. Yes, and the mass inside the control volume is decay. Okay, so this is we always this is a general form, but we operate by the integrations. This is our continuity equations, and we can also rewrite it by the sigma. And please notice that this is for the pipe flow systems. The pipe flow systems, we also no need to have the mass in the volumes. This item will equal to 0 for the pipe flow systems. We will provide more detailed introductions for these systems. So we just, for this table, we just notice that two continuity equation formulas. The one is use the integration operator, another use the summations. Okay, so the following slide, we have many exercises. So we just have a 10 minutes break and then we go back to find the answer for the following exercise. Okay.